Good morning. Now, in today's class, we will learn about Heisenberg and Schrödinger. Heisenberg was a German physicist, and he has made his reasonable contributions to the field of quantum theory. And he was one of the most important figures in the development of quantum mechanics and its modern interpretation. So, most of the works of Heisenberg was concentrated on the field of quantum mechanics. So he also developed matrix mechanics formulation of quantum mechanics, and he also developed the very famous uncertainty principle in 1926. Then some other areas that he has made his contributions was in the area of hydrodynamics of turbulent flows, atomic nucleus, ferromantism, cosmic rays, and subatomic particles. Now, Dirac in 1928 has derived his relativistic wave equation of quantum mechanics, and that actually implied the existence of a particle called positive electrons, which is later called by the name positrons. That is, in 1932, it was Anderson who, through his experiment using a cloud chamber, he has detected the presence of positrons in cosmic rays coming from a sun. Okay, so Dirac, he just indicated the existence of positive electrons, and it was Anderson who actually detected that such a material exists, that is positrons or positive electrons exist in cosmic rays. Then Heisenberg, he interpreted this Dirac equation, and he found that it has got a spin half. Then he also made reasonable contributions in the area of electromagnetism, and then he has developed some relativistic quantum field equation. Those equations helped us to detect the possibility of existence of a particle and its creation and destruction. He also laid foundation for relativistic quantum field theory. Then he was very instrumental in planning nuclear reactors, and as well as a research reactor, and he was the principal scientist in the German nuclear weapons program during Second World War. Now these are some of his remarkable contributions. One is the Copenhagen interpretation. Uh, it is nothing but an expression of meaning of quantum mechanics. Now according to this Copenhagen interpretation, physical systems do not have definite properties even before it is being measured. That is, before measuring any physical system that you take will not have any definite properties. Then, and quantum mechanics can only predict the probability distribution of a given measurement's possible result. So Copenhagen interpretation is nothing but it is an expression of meaning of quantum mechanics. It states that even before you are measuring a physical system, that system will not have any definite properties. Now, this quantum mechanics, what it can do is that it can only give us an idea about the probability of distribution of the possible results of a given measurement. Okay. Now, the act of measurement will affect the system, that is, it will reduce the number of possibilities into a single value. That is, it will allow a set of probabilities to reduce to only one of the possible values. That is what the measurement actually does. That is, it reduces a set of probabilities, that is, many probabilities, into a single possible value. Okay, so after measurement, even before measurement, you will have a set of probabilities. That means you will have a set of values. But once a physical quantity is measured, you will be getting only a single possible value. And that feature is known as wave function collapse. Now, another area is that is of interest was matrix mechanics. That is, at the age of 22, he received his doctorate from University of Munich, and later he carried out his research work, and it was at that time, that is during his research work, that he developed a matrix mechanics, and which is a form of formulation of quantum mechanics. It actually was the first complete and correct definition of quantum mechanics, matrix mechanics. Okay, that was the first complete and correct definition of quantum mechanics. Later, he has extended this matrix mechanics into many of his research areas, especially in the physical properties of particles. Then, next is his one of the important contribution, that is development of a principle, that is uncertainty principle. It states that it is impossible to know both the exact position and the momentum of an object at the same time. That is, if you have an object, it is impossible for you to detect the exact position and its momentum at the same time. So let delta x be the uncertainty in the measurement of position, and delta p be the uncertainty in the measurement of momentum. Then its product, that is delta x dot delta p, is found to be greater than or equal to Planck's constant h by 4 pi. So that was the principle. Then he was awarded a Nobel Prize in Physics in 1932 for the creation of quantum mechanics, and that actually led to the discovery of many allotropic forms of hydrogen. He has shared this prize uh, with uh, with the collaboration on matrix mechanics. Then what these are some of he became the director of Max Planck Institute for Physics, and later he became the director of Max Planck Institute for Physics and Astrophysics, and he has continued his research work, and he has published a lot of research papers on superconductivity, turbulence, cosmic ray showers, etc. And he was appointed in various councils, commissions, associations, and he has received numerous honors and awards. Next is about Schrodinger. He is an Austrian theoretical physicist, and he also was very famous for his contributions in the area of quantum mechanics, just like Heisenberg. And he was awarded Nobel Prize in Physics in 1933 along with Schrodinger and P.A.M. Dirac for the discovery of new productive forms of atomic theory. He was awarded doctorate in 1910, and he has published many research papers, and he also served in military, uh, and later he became a physics professor in 1921, and he remained there for 6 years. Now, some of the most important highlights was his series of 4 papers, research papers that he has published, and those papers covered the areas of modern quantum mechanics, and these 4 papers dealt with the following. The first paper was on wave mechanics. In that, he discussed what is known as Schrodinger equation. That is an equation that describes how quantum state of a physical system changes over time, and it also give the correct energy agent values, especially for hydrogen like atom that possess 1 electron. Then his second paper was actually involving a solution, or it actually a paper solving wave equations of quantum harmonic oscillator, rigid rotor, and diatomic molecule. And the third paper actually showed the evidence of his approach to Heisenberg's matrix mechanics, and in that he discussed about Stark effect. Stark effect means it is actually a process of splitting of spectral lines under the influence of a electric field. Then his fourth paper describes how to treat problems in which system changes with the time. One such problem is the scattering problem. Now, wave mechanics, that is one of his major contribution. That is, in 1926 he developed wave mechanics. It is nothing but a relationship between the motion of a particle that exhibits wave-like properties, just like electron, and its allowed energies. Now that Schrodinger equation was given like this. Uh, that is, it actually describes the behavior of system by a wave function, and that equation is known as wave equation. It is known as Schrodinger equation, given by I h cross dou psi by dou t is equal to minus h cross square del square by 2m plus v psi, e psi equal to h psi. Okay, here E is the energy, h is the Hamiltonian operator, and psi is the wave function. Next is an illustration that is about his Schrodinger's cat, and uh, it actually presents a hypothetical cat that may be simultaneously both alive and dead. That is a state of quantum superposition. What he does is that uh, a cat is placed in a steel box along with a Geiger counter, then a poison, hammer, and a radioactive substance. Now, when this radioactive substance decays, the Geiger counter will detect the presence of radioactive rays, and once it is detected, it will trigger the hammer, and this hammer will break the vial to release the poison, and that poison will kill the cat. So, as a radioactive decay is a random process, there is no way to detect or predict when it will happen. That is unknown, or it is a case of uncertainty. So, what we can say is that until the box is opened, an observer doesn't know whether the cat is alive or dead. Why? Because the cat's fate is intrinsically tied to whether or not the atom has decayed and the cat would. Okay, so until the box is opened, it is not possible for us to say whether the cat is alive or dead. Okay, that is, the cat state or the state in which the cat exists is completely unknown, and therefore, according to Copenhagen interpretation, the cat is considered to be both alive and dead at the same time. Okay, so immediately upon looking at the cat, an observer can say whether the cat was alive or dead, and the superposition of the cat, that is the idea that it was in both state, that is both alive and dead, would collapse into either the knowledge that the cat is alive or the cat is dead. So it is not possible for us to say whether it is alive or dead at the same time. Okay, so that is called by the name Schrodinger paradox, that is the state of existence of a thing in both states. Here he has illustrated it with the example of a cat. So this quantum superposition, that name is also called by that name. Either it is called Schrodinger paradox or quantum superposition. Okay, so it is mainly useful for illustrating the quantum mechanics of wave particles or point particles, but it is not applicable in the case of large objects. Okay, why? Because it is not possible for an organism to be simultaneously alive and dead. That is in the case of lively objects. Okay, so in that, we have to describe the contributions. One is Schrodinger cat, Schrodinger equation, wave mechanics, then highlights of his 4 papers. Okay, that is in the case of Schrodinger. In the case of Heisenberg, just a brief theory about his early life, then a special mention on uncertainty principle, matrix mechanics, Copenhagen interpretation. Okay, that's it for today. Thank you.